Hello everybody. Because the lecture on Friday wasn't recorded properly, I've decided to re-record the lecture and upload it. So let's start off. On Friday we introduced the concept of an exponential function, so let me go through the basics. So exponential functions. Okay, so first of all I want to go through the laws of exponents. These are very important. They're used all the time in arithmetic and basic algebra, and it's important you know them all. Laws of exponents. So I'm going to fix some numbers. Let's have A, B, and C numbers. And I'm going to make the assumption that A is not equal to 0. If A is equal to 0, some of these kind of don't make sense, so I'm just going to avoid that case entirely. So first of all, I want to kind of go through the basics for simple values of exponents. So A to the power 1 is equal to A. Second, a bit more general than this, if I have A to the power n, where n here is going to be a positive whole number, this is equal to A times itself n times. Okay, so it's worth pointing out here, n is a positive whole number. So it's 1, 2, 3, 4, so on and so forth. Okay, so we've got that. There's one case that I'd like to talk about here. I mean, A to the 0. What does that mean? So that, by definition, is just going to be equal to 1. So these are our core basic operations. The next is how do they interact with things like addition and multiplication? Well, an important one is A to the B plus C is the product of A to the B and A to the C. Okay, extremely important. Next, A to the B times C. That is equal to A to the B all to the power C. Next, fifth property, if I take the product of A and B and I raise it to the C, then this is equal to A to the C times B to the C. And finally, kind of a useful rule to know, A to the minus B is equal to 1 over A to the B. So I can switch an exponent as long as I'm willing to switch it from the numerator to the denominator in a fraction. So these are all extremely important. You need to know all of these facts. Very important. They turn up all the time. And just a warning at this point, a very common error I see, which is kind of disastrous, especially if it's in an exam, if you make the following mistake. So warning, if I have A plus B to the power C, that is not equal to A to the C, not equal to A to the C plus B to the C, not in general. So just as a quick example, e.g., just to illustrate, if I had 1 plus 1 squared, so to the power 2, this is equal to, well, obviously 2 squared, you do the brackets first, and that's equal to 4. However, if you were to try and use the above, 1 squared plus 1 squared is equal to 1 plus 1, which is equal to 2, and that is not equal to 4. So you can see this can't possibly be true in general. So these rules are incredibly important. They turn up all the time. It's important you can deploy them accurately, especially in situations when you're doing things like exam questions. Many questions in exams will have the form. I mean, you'll be given potentially quite a complicated function, and you'll have to do some operation on it of some description. And it'll be very difficult given the way it's presented to you. But if you use some of these rules to simplify things, the problem will become much easier. That's a common way in which you're going to have to use these things. Okay, so those are the basic laws of exponents. Okay, so what's an exponential function? So let's fix for the moment. Let's fix a number, A strictly greater than 0. So the exponential function with base a, by definition, this is equal to the function a to the power x. So this looks very similar to a power function, but there is a big difference. You see here the base, so this thing is called the base. The base here is a fixed number. In a power function, the base is varying. This thing on top is called the exponent. So in an exponential function, it's the exponent that is a variable and it's the base that is fixed. In a power function, it's the other way around. It's the base that's a variable and it's the exponent that is fixed. These are two very different types of functions. So what do the graphs of these look like? Well, it depends a little bit on the value of a. So let me kind of just draw a picture. So I want to give you kind of a broad general shape of all exponential functions or their graphs. So let me attempt to draw. So let's take this as the x, as y is general. Okay, so let's assume that a is greater than 1 for the moment. What is the general shape of this? Well, remember what the exponential function is. If a was bigger than 1, and I was to put a value of x, which is the positive whole number, I would be multiplying a by itself many times. And if a is bigger than 1, that means the graph is going to grow, or sorry, the function is going to get larger and larger and larger. 2 squared, 2 cubed, 2 to the power 4, it's growing very fast. So this basically means if a is bigger than 1, the graph is going to grow very quickly as I let x increase. So the basic shape is the following. I'll try to draw this reasonably accurately. So it rises up like that, and it continues to grow. It gets steeper and steeper and steeper. So this is the picture, y is equal to a of x, under the assumption that a is strictly bigger than 1. And it's worth kind of pointing out what happens for different values of a. So for a different a, I'll get a different graph. I think we should maybe just say here that this kind of gets steeper. Gets steeper for bigger values of a. So if I was to graph on this one thing, let's say y is equal to 2 to the x and y is equal to 3 to the x, because 3 is bigger than 2, they would look very similar in shape, but the 3 to the x would be growing more steeply than the 2 to the x. Now what about, on the other hand, if I was to choose something where a is strictly less than 1? Well, it would basically be exactly the same picture, but reflected in the y-axis. So it would kind of look like this, getting steeper like this, dot, dot, dot. So this would be the picture, y is equal to a to the x, under the assumption that a is strictly less than 1. Why is this the case? Well, again, just think about it for positive whole numbers. As I have a positive whole number getting bigger and bigger and bigger, if a is less than 1, then if I multiply it by itself many times, I get really small. So for example, if a is equal to a half to the power 5 is a half times a half times a half times a half times a half. That's going to get really small the more I do it. So that's the reason it's getting closer and closer to 0 as I allow x to increase. There is one anomalous case, which is kind of a bit an outlier here. What about if a is equal to 1? If a is equal to 1, then we just have kind of a silly graph almost. Y is equal to 1 to the x, and 1 to the x is just the constant function 1. So this is an outlier. It's not very interesting. It's not really something we ever consider when we're discussing exponential functions. Okay, so from this picture, we can see a few things. First of all, the domain of the function, at least in the case when a does not equal 1, if a is equal to 1, the graph is very different, so obviously we have a different domain. If a is not equal to 1, the domain is equal to, well, it's everything. In fact, no, what am I talking about? This is silly. The domain isn't the issue, so the domain is always the same in all cases. So regardless of a, as long as it's strictly bigger than 1, or sorry, strictly bigger than 0, I can feed in any value of x. So the domain is all real numbers. A to the x always makes sense as long as a is greater than 0. At this point, it's maybe worth mentioning, this is a big reason we don't choose a to be negative. If a is negative, then we have real problems considering what the domain is. For example, if a was minus 1, then if x is equal to a half, let's say, that doesn't make sense. Minus 1 to the power half would be the square root of minus 1, which doesn't work in the real numbers. You can't take the square root of a minus number. So we completely avoid the issue of negative bases because it makes the domain very, very confusing. So when we talk about exponential functions, we always assume, remember, that a is strictly greater than 0. Next, range. Well, this is where I do need to make choices or a restriction on a. So let's have a not equal to 1. If a is equal to 1, this is the constant function 1, so the range is just a single element set 1, so uninteresting. But the range, if it's not equal to 1, well, we can see from the red and the blue lines that we seem to be able to get any possible strictly positive number. So the range is equal to, in interval notation, 0, not inclusive of 0. A to the x is never equal to 0, but it's any positive number from that point on. So that's the domain and range of exponential functions. So what I want to do now is to talk about a very specific application of this, which is going to kind of turn up many times in the future and illustrates how exponential functions can appear in, let's say, unexpected places. So let's talk about something called compound interest. It's the kind of thing all of us have heard of. And it's always kind of confusing. You often get given to you in just kind of a, here's a formula, do it, don't think about what's happening too much. What I want to do is to kind of really carefully pick apart the meaning of compound interest. So compound interest is the idea of, let's say you have some sort of bank account and you put a certain amount of money in at the beginning, okay, at time t is equal to 0. Then what the bank does at fixed intervals of time, it adds interest. And the amount of interest it adds depends on how much money was in the account 1 unit of time before. So this is kind of confusing. It's easy to get kind of lost. We need some notation to make sense of this. So let's start off with P. Let this represent the amount in the savings account. We'll say it's a savings account. At time t is equal to 0. Okay, so t almost always represents time in a practical problem. Very nice. Next, well, the amount of money that's going to get put into the account at each of these fixed intervals of time has to depend on something, and it depends on something called the interest rate. So very often, if you open a savings account, take out a loan or anything like that, you're told the interest rate, which will be given to you as a percentage. So that's going to represent kind of how much of your deposit is going to be added as a percentage over time, roughly speaking. So I want to represent this using a number. I'm going to call it R, and I'm going to call this the annual interest rate. And often, as I said, the interest rate is given to you as a percentage. It's more sensible for us to give it not as a percentage, but as the equivalent number between 0 and 1. So R is going to be less than or equal to 1, greater than or equal to 0. So just as a sanity check, if we have 5%, that kind of corresponds to R is equal to 0.05. Okay, so if you're used to the idea of using a percentage for an interest rate, we're just converting it, we're just dividing it by 100 to get a number. So what we want to understand is how the balance in the account changes over time. So to do that, I'm going to need a function to represent the account balance. So let's call it f of t. Unsurprising. Let this be the balance in the account at time, let's say t. And I want t to be in years. Notice I gave you the interest rate as an annual interest rate, whatever that means. That means somehow the interest rate is tied to yearly intervals. So when I talk about the time, I should talk about it in years. That would be the sensible unit to choose. Okay, so let's gradually build up the meaning of compound interest. So, so from the notation, f of 0 is equal to p, right? That's the initial deposit. That is how much money is put in the account at time 0. What about at time 1? So at time 1, so here's the plan. At the end of every year, interest is going to be added. Banks often call this compounding. So compounding means you add interest. So we're going to compound in annual intervals. So every year, at the end of the year, we're going to add interest. So here's the basic plan. After 1 year, I look at how much money was in the account a year ago, so f of 0, so that would be p in this case, and then I add r% of it. So because of my convention on r, that would be r times f of 0. So just to put this into words, this is kind of the balance a year before, and this part is just the interest. So I look at how much money was in the year before, and I add that percentage of it to the account. So of course we have notation to simplify this a little bit. Writing f of 0 is a nightmare. This is equal to p plus rp. And I could write this, I suppose, as, well, I can take a factor of p out. I'll write it like this, p times 1 plus r. That's a nice way to write it. It's not obvious that's the most sensible way to write it yet, but let's stick with it. Okay, so that's after 1 year, 1 unit. So I'm compounding at the end of every year. Next, what about f of 2? Well, we have exactly the same logic. It would be the amount in the account a year before plus the interest, which would be r% of the amount in the year before. That's how compound interest works. So this is what makes it so confusing, because the amount you're adding each time changes depending on what was in it the year before. So let's now just replace f1 with this. Okay, so these are the same. So what does that give me? So I'm just going to blindly go through this. This is going to be p times 1 plus r times p times 1 plus r. Now that's a nasty looking piece of algebra, but let's look closely at this. I think we have, so I'm going to use lots of colours here. This number here and this number here are exactly the same. So I can pull off the same trick as above. I can pull out a factor of p times 1 plus r. And if I do that, what do I get? Well, just to really illustrate this thing at the front, it's silly to write this, but it's worth writing down for the algebra. This is 1 times this. So if I was to factor this out, this would become 1 plus r. So that's coming from the 1 and the r in front of this term, multiplied by p times 1 plus r. So now I can rearrange this, and I get what? P times 1 plus r all squared. So you see there's a pattern emerging, it strikes me. What we have is, we've compounded once, that corresponded to multiplying the initial deposit by 1 plus r, and we've compounded a second time, and that corresponds to multiplying it by 1 plus r twice. So if we went through exactly the same procedure with f of 3, did all of this simplified, this would turn out to be equal to p of 1 plus r to the 3. And you can probably guess what's going to happen here. At this point, if I keep doing this, f at time t is going to be equal to p of 1 plus r all to the power t. So something to be said here is this amount, I mean, the t has to be a whole number for this truly to make sense. So this is t as a whole number. T is a whole number. So let's just have a think about what that actually means in terms of the balance in our account over a given period of time. Let me draw a little picture to illustrate this. This will be a rough sketch of the account balance over time. I want to show you something about this which makes life kind of difficult. So this is going to be the balance versus the time. Now let me mark some points on the bottom. I don't know, let's say 1, 2, 3, 4, so on and so forth. So what do I have? Well, so let me draw this in blue to make it obvious. At time 0, so let me write 0 here. P is put in at time 0, so this point here, we'll call it this point here, we'll call it P. Inclusive. Okay, so for the first year, your balance is P, nothing changes. Right, it's all exactly the same, up until you hit 1. And then suddenly, you jump, right? A certain amount gets put into the account, and then it stays the same for another year. So the amount that gets put into the account, well, you just multiply P by 1 plus R. So then it's the same for another year until you hit 2, and then suddenly there's another jump. You multiply by 1 plus r. Same basic deal. And at the end of the third year, oh goodness, this is terrible. Let me try to make this a little bit more sensible. So I actually want them to match up. So let me try doing this properly. Is that roughly right? That should be above 3. Okay, so at 3, same deal. We're going to jump another amount, so it's going to kind of jump a bit further. So this would be what the account balance looks like. It's basically static, and then at the end of every year it jumps. So this means the graph is pretty hideous. We're used to drawing graphs of functions which are nice kind of reasonable curves where I don't take my pen off the page, but this one is jumping, which makes it quite difficult to deal with. So that's one of the things about this procedure which is going to be quite difficult to deal with mathematically. So what I want to try to do is to come up with a way to compound interest and make it a bit less jumpy like this. So let's think about, instead of compounding at the end of every year, let's try to compound more frequently. So can we come up with a way to compound at smaller intervals of time? So that's the basic question. So let's try and, so let's now compound, let's say m times in a year. So what I did a moment ago was m is equal to 1. We compound once at the end of every year. If m was 2, we'd be compounding every 6 months. M is 12, we'd be compounding monthly, 365 daily, that kind of thing. So let's just go through the same procedure. So we're going to use the same essential formula as above, but it's going to look a little bit different. So again, f of 0 is the same, it's p. But then what? Well, let's just do the same interval. So let's do f of 1. After 1 year, I'll have compounded m times. Now, the interest rate was given annually, so it wouldn't make sense to compound using the interest rate r at each one of my smaller intervals. That wouldn't make sense. Instead, what we should do is compound with a rate given by r divided by m. So each little interval will correspond to an interest rate r divided by m. That makes sense because the interest rate r is meant to be for the whole year. So what have we got? We've got p, and then we need to compound it m times, but with respect to a different interest rate. So this is going to give me 1 plus r over m. So bear with me a second. So that would correspond to compounding once with this new interest rate, r divided by m, but I need to do it m times, so that means I need to raise this to the power n. So this is kind of a scary looking formula, but it represents compounding n times with respect to the annual interest rate divided by m. Okay, so what about f2? Well, same basic principle. It would be exactly the same deal. It would be p 1 plus r over m. But now what I do, well, I'm compounding it 2m times, so it would be 2m in the exponent. 2m because we go over 2 years. Nice. If I had 3, you can probably guess. This is equal to p times 1 plus r over m, 3m. So you can kind of see what's going on here. We're counterbalancing two things. We're compounding more frequently, but we are shrinking the interest rate, essentially. So there's kind of a counterbalance. We're dividing the interest rate by m, but then we're compounding m times. So they're kind of balancing each other in some way. So in general, f of t, if we look at the pattern that's emerging, it seems to be the case that we've got t is 1 plus, or t is p times 1 plus r over m to the power tm. And again, if we're going to use this, I suppose, just to be really safe, we want t whole number here as well. Really, you don't need t to be a whole number. It really has to be an integer, so a whole number divided by m. That works. So imagine if I was now to try to graph the balance versus the time. It would look kind of similar to the graph above, but it would have more steps in it, essentially. It would kind of follow the same shape, but there would be more jumps. There would be a jump every nth of a year. So it would look a bit less, it would look a bit more continuous, maybe is what I'm saying. It would kind of jump in smaller intervals. So here's a really interesting example. Let's think about what happens in the following case. So this example is going to be interesting from two perspectives. It's going to introduce us to a really fundamental new number in mathematics that you may not have seen before, one that kind of looks very strange if it's just given to you without any motivation. In addition to this, it's going to introduce us to an idea which is going to provide the backbone for lots of future concepts, the concept of a limit. Okay, so here we go, important example. Important example. I can't really stress how important this is. It's ridiculously important. Let's do the following kind of crazy situation. Let's have P is equal to 1, and let's have R is equal to 1. So you're investing $1 in an account, if you want, and the interest rate is 1. And that corresponds to 100% interest rate if you're using the usual notation. So what I'm going to do is try to work out what happens as I allow the number of compoundings to increase throughout the year. So we'll start off with m is equal to 1. If m is equal to 1, well, let's just take this formula. So we're going to repeatedly use this formula, right, over and over again. So we've already got p is 1, we've got r is 1, now we need m to change. So if m is 1, this tells me that, what does it tell me? It tells me that at time f1, so I'm only going to look at how much money is in the account after a year, just for simplicity. 1 plus 1 to the 1, that of course is equal to 2. That makes sense. 100% of 1 is 1, add that to your initial balance, 1 plus 1 is 2. Great, okay, that's a pretty awesome deal. Next, m is equal to 2. Well, if we're compounding twice, we compound twice with respect to 50%, so this would be f of 1 is equal to 1 again, that's your p, times 1 plus 1 over 2 squared. Now that would be 3 over 2 squared, it's a bit nasty, but it's equal to 2.25. So let's just do a little bit of a sound. What does this actually mean? I mean, what it means is if a bank comes to you and says, I've got interest rates 100%, should I compound once or twice? You should compound twice, right? If you were given the option. Compounding twice seems to mean at the end of the year you get more money. Okay, so this is interesting. It tells you that if a bank comes to you and says, I have the following interest rate compounded this frequently and another interest rate compounded frequently but in a different way perhaps. So one maybe is compounded quarterly, one maybe is compounded monthly. That'll make a big difference to how much interest goes into your account. So this is interesting. Immediately we see there's something a bit subtle going on. Next, let's do m is equal to 3. So now that seems like a reasonable choice. So if m is equal to 3, f1 is equal to 1 times 1 plus 1 over 3 to the 3. So again, it's kind of a nasty number in decimals, but roughly speaking, it's 2.37. Again, we see I should compound more frequently. It seems to me that I get more money if I allow the compounding to happen more frequently. So now let's jump a few terms. Let's do m is equal to 8. If m is equal to 8, at time 1, this is equal to 1 times 1 plus 1 over 8 to the 8. So this is getting a bit of an awkward calculation. Turns out this is equal to 2.5658. Okay, so every time it's gone up. So I think at this stage, one's instincts should be the following. It strikes me as m increases, the amount of money in your account after a year is getting bigger. It's very natural to assume here that if I allow m to get bigger and bigger and bigger, like really big, maybe the amount in the account is just going to grow and grow and grow. So I'm going to be able to get as much money as I want. Let's jump ahead then. Let's go to 1,000. So that's a hell of a lot of compounding. If you do this, well, f of 1 is equal to 1 times 1 plus 1 over, goodness, is it 1,000 to the power of 1,000? So obviously you need a calculator to do this, or a computer. Turns out this is equal to 2.7169. Interesting. So yeah, it's bigger, but it seems that the increase has slowed down tremendously. We've gone from 1 to 8, we're jumping by 0.56, whereas 8 to 1,000, we're jumping by less than 0.2. So it seems that we are increasing, but at a much slower rate. So let's really do a massive jump now. let's do m is equal to 100,000. So this would be compounding very frequently. So if f is equal to 1, f of 1 now is equal to, it's the same basic formula, 1 plus 1 over 100,000, all to the power of 100,000. So this would definitely require a computer. This actually isn't that different. It turns out to be 2.7183. ... So there are more numbers. But we're seeing something happen here. As m gets bigger and bigger and bigger, the expression that I'm feeding it into, so this let me get this right. So this expression, so I've got my m here and it's being fed into this. It strikes me that as m gets bigger and bigger, this number isn't growing without bound. It's getting closer and closer to some constant, something strange, as number 2.71 something. So it turns out the following is true. So this is a remarkable fact. So definition. So this is why it's such an important example. So definition, so let's say x, so x is a variable, as x becomes larger and larger, the quantity, which I'll say, I'm going to use the same expression as above, 1 plus 1 over x to the power x. So that kind of funny looking expression there, this gets closer and closer to a fixed constant. And it's a weird constant. We're going to call it E. We're going to call it E. And there are two ways of thinking about this. E for exponential, maybe, if you want. Historically, though, it's based on E for Euler. So Euler was a great mathematician from the 1700s. I know it seems strange that, I mean, Euler, you'd think it would start with an O, but Euler is actually spelt, this is a historical side note, kind of from Euler. So it's a strange name. You might think that's pronounced Euler, but it's actually pronounced Euler. So he was the person that really discovered this constant. And if you want to know what it is, it's a little bit like pi in the sense that as a decimal, it's not very pretty. But you can kind of guess roughly what it is now. So if you look at the kind of m is equal to 100,000 up here, that's actually not bad. The constant is 2.718281828. It's just a fluke that it repeats in that block. It keeps going and it's kind of like all over the place, just like pi. It has one of these like infinitely long decimal expansions which is kind of bouncing all over the place without any obvious pattern. So this is a very interesting thing. All we've done is thought about compound interest. That's it. And I've allowed myself to compound more and more frequently, all very down-to-earth, simple concepts, and suddenly I have this bizarre constant appearing, something between 1 and, something between 2 and 3, with a weird decimal expansion. So concretely, you should think about E as, I mean, the amount of money in your account if I allow myself to compound it bigger and bigger, or more and more times throughout the year. So you put $1 in an account, the interest rate is 100%. The more frequently I compound, the closer I get to E at the end of the year. Very strange. Okay, so what about, so this is kind of this looks very strange because it looks, I mean, we've only done one case. We've done P is equal to 1 and R is equal to 1. That's very restrictive. What about if I was to choose, so question, what about if we go through this procedure for, what about for different, let's say, R and P, right? So we had R as 1 before and P as 1. Do I have a similar kind of way to think about what happens as I compound more and more frequently? So let's kind of go through the same procedure. So this is more difficult. I think this is one of the most difficult things, certainly in this lecture, but it's a precursor to what we'll be doing certainly next week and beyond. So first of all, let's have f of t. So let's imagine I'm compounding. So I put a deposit of p in, I have an annual interest rate r, and I compound m times. If I compound m times, the formula we've got is P is what? It's 1 plus R over M to the MT. I think that's what the formula was. Okay, so let's take a look at this. So what I want to do is I want to allow M to get bigger and bigger and bigger. That's the basic plan. And I want to try to relate it back to what we've just done. The reason for that is because I've just worked quite hard to understand a specific case and I've got this kind of interesting piece of information from it. Can I somehow incorporate that piece of information into this situation where R and P are not necessarily equal to 1? So here's the basic plan. You see the formula above, this guy here. What I want to do is to rearrange the formula for f of t to make it look more like that. In particular, I would like to rewrite the fraction r over m, first of all, so I want to basically, so let me kind of match things up here. So you've got a hallmark of this equation are kind of the 1 over x here. So I need this thing here, to match in some way, but it's not going to match unless r is equal to 1. So I've got to do a bit of algebra or some gymnastics. I need to match those up, so here's something I'm going to do. So this is equal to, I'll keep that above, this is equal to P times 1 plus, and this is going to look silly, but I'm just going to go through it, M divided by R. So I'm rewriting that with the R on the bottom. That's the basic laws of arithmetic. So it looks kind of strange, but notice it's now the correct format. It's 1 divided by something. Okay, so kind of in my head, what I'm trying to do is to rearrange this. Yeah, what I'm going to try to do is to rearrange it. So rearrange to make, rearrange to have, let's say x is equal to m divided by r. I think that's what I want to say here. I'm going to try to write this thing on the bottom in the form 1 plus 1 over x to the power x, so the thing above the green line, and to do that I'm going to have x is equal to m over r. So now let's take another look at the top formula. The top formula, it has another thing in common, so it's 1 over x, but also this thing here and this thing here have to be the same. Right? If I want to use what I've just done, I need to have what's in the denominator and what's in the exponent to be exactly the same. Now down below, notice what's in the denominator is m over r, but this guy is not the same. mt is not necessarily equal to m over r. So that means I'm going to have to somehow algebraically manipulate this. So this is a bit of a dirty trick, but bear with me. So I want to have an m over r in the exponent. So what I could do is divide through by r and multiply through by r simultaneously. It's like doing nothing. It's like multiplying by 1, but it'll allow me to rewrite in a slightly different format. So as I said, this is difficult, but it's worth going through. So I'm going to do, 1 plus 1 over m divided by r. And then, yes, I'm going to do m divided by r here times rt. So don't look at this and say to yourself, oh, obviously this is the right thing to do. This is quite a complicated procedure. As I said, what I'm trying to do is to rearrange this bottom formula to make it like the top formula. And this is just a kind of a dirty trick. It's the kind of thing that you have to see a few times before you kind of internalize it. So what have we got now? Well, this is good. Just as above, the way I've written this and this now match up. So that strikes me that I'm going to be able to use the definition above, potentially. So let's go through this carefully. So laws of exponents, I can simplify this again. So what is this equal to? So now P, so I've got a product in the exponent, so I can break that into the following. 1 plus 1 over m divided by r, the power m over r. All of that to the rt. Okay, so let's just have a look. Why have I done this? Let's go back to the formula above. Can I fit these both on yes? This now, inside the bracket at the bottom, fits perfectly with the thing on top. Right? It's a 1 plus 1 over x, all to the power x, where m is equal to, well, x is equal to m divided by r. So notice, if I allow m to get bigger and bigger, m over r is going to get bigger and bigger. So as m grows, m over r grows. Hence, well, the thing in the bracket's going to get closer and closer to e. So 1 plus 1 over m divided by r, all to the power m over r, gets closer and closer to e. Okay, so let's conclude. If I'm working out the balance, so I'm interested in the balance at some time, I'm interested in this. I have a fixed r and a fixed p, and I'm interested in what happens as I allow m to get bigger and bigger. What seems to happen is, as m gets bigger and bigger and bigger, if I rewrite it in this format, it's p times this all to the power rt, and this thing above the blue line is getting closer and closer to e. So the conclusion, I think, is the following. It's a remarkable conclusion, considering all we're doing is working out some compound interest. So the conclusion is the following. As m increases, i.e. we compound more frequently, f of t, the actual amount in the account, gets closer and closer to, well, it seems to be p times e all raised to the rt. Remarkable. So this thing here is a true exponential function. It makes sense for any value of t, so we no longer have kind of steps or anything like that. This is a true exponential function. And maybe I could say, I mean, just as an aside here, this maybe looks a little bit different than an exponential function, but remember, this is equal to p times e to the r times t. So the base here, if you want, is e to the r, if you want. Right? So the interest rate does change what the base is. But e is intimately related to this. Right? It's really, really interesting. This number e seems kind of crazy, but it seems to tell us what happens as I compound more and more frequently. So some banks decide that rather than compound in fixed intervals, what they're going to do instead is actually take this formula as a way of determining how much money is going to be in the account. And because the formula is derived from compounding at smaller and smaller intervals, it's like you're compounding all the time, essentially. So you're continuously compounding. So continuous compound interest is where the account balance is given by this formula. So let me write that down. So continuous compound interest. Continuous compound interest. So if a deposit let's say of p dollars is invested in whatever savings account, invested at annual interest rate let's say r, which is to be compounded continuously. So this is what continuous compounding means, to be compounded continuously. Then the amount in the account, by definition, is this function above. This is what the bank uses to determine how much money is being put into the account. So again, this f of t is the balance in the account. So this is very interesting. When you're given the information about a savings account, or a loan or something like that, you're told about annual interest rates. But just as important as that is the information about when compounding occurs. If it's compounded in fixed intervals, that will make a difference to how much money ends up in the account, as we've seen before. And the most extreme case is when they compound continuously. So it's like they're continuously adding interest the entire time. The benefit of this approach is the bank can keep track of how much money is going to the account all the time. There are no jumps in the balance. Beneficial to you as well as the person in the bank account. And it basically is going to mean the function is going to be nice from the perspective of the graph. So the graph is going to be a nice, smooth exponential function without any kind of jumps in it. So it's going to make life much easier for us. So it is really genuinely true there are banks who can compound continuously. So it's something to kind of understand. It's really interesting. People who work in more sophisticated financial markets, they compound continuously as well. So this is used all the time. So it's not just some sort of mathematical abstraction without any basis in reality. It really is used by people in finance and banks to determine how interest works. I think the major takeaway about this is it's the number E is absolutely remarkable. This weird constant 2.7 ... seems to be intimately related to compound interest, which just doesn't seem believable almost. But it illustrates that if you take something and try to pick it apart slowly, methodically, sometimes really unexpected things appear, and this number E is a perfect example. So, it's a good place to stop.